start with this, that Brownian motion. Well, actually it goes this way. Limit of a random walk is Brownian motion. So let's consider a simple symmetric random walk. And so you have in the random walk, that means we have variables x1, x2, x3, so on, where these 1, 2, 3, they indicate the number of steps. Right, so this variable takes values +1 or -1. So you are taking a step to the right or to the left. And it's symmetric, so your probability over here is half. Similarly, probability here is half. Now, what you normally do, you make this variable, which is simply the sum of first n steps, and it tells you where you are after n steps. So this becomes your desired random variable. Telling you how far you are from starting position. But now suppose you want to keep track of time as well. And now suppose you take a step every delta t time. We take a step every delta t seconds or minutes or whatever. So you are taking these discrete steps, but you are just keeping track that each discrete step comes after a delta t time, because you're not going to make it a continuous process. So when this delta t becomes very small, then it's going to become kind of a continuous walk. So you take every delta t units of time, you take a step, and the step size, because we're going to make it very small. So if we take finite or a large step every delta t units of time, we will be making this variable will blow up. This will become very, very large. So we give a step size. So we take a step every delta t units of time of size delta x. That means given this, we can define then after time t, the displacement will be given by the variable t, which would be delta x step. In the first step, you will cover delta x displacement, and x1, if it's +1, you displace to the right. If it's -1, you displace to the left. Or you're increasing the step, you're going forward and backward, depending on if x1 takes a value of +1 or -1. So these xi, they still take these values, again with these probabilities. But you have these step sizes. How many steps you take? Well, you have waited till time t. So, and at each time delta t, you take a step. So your steps would be approximately t over delta t. To be precise, you can say that n is this number, which is the largest integer less than or equal to t over delta t. But if t is large enough, delta t is small enough, it doesn't really matter. You can just, well, it's still this integer you are after, but I can just think of it as just this division and neglect the decimals you get. So that means over here, I have this number n. So this s of t, I can give this label n, where n is this thing. Now, when this n becomes very large, so when delta x is very, very small, well, for now, delta t is small, and then we will see we'll have to make delta x small as well. But if delta t is small, if delta t is very small, then n becomes very large. Then we have a sum of identical random variables. A sum of a large number of identical random variables. That means we can apply the central limit theorem. So just a reminder, what does the central limit theorem says? Says that if you have the identical means identically distributed random variables with mean mu and variance sigma square, then if we define this variable, then this thing is a standard normal variable. Or in other words, this is same as saying Sn is a normal distributed with mean and mu and standard deviation sigma under root n, which is same as saying variance sigma square n. So the summed, if you take a sum of these variables, n of them, and n is very large, then this variable is normally distributed, and you also know its mean and its variance. This same thing I can also write equivalently. One can say that Sn as distribution given by And this is the standard normal. So this is simply equal to what I had over here, n mu, and this is simply equal to sigma under root n. So now what we have, we're going to apply this theorem, and we have this sum. So to apply this, we need to calculate. So we know that when n is going to be large, it's going to be some kind of a normal variable. And to find it properly, we just have to find its mean and its variance. So now we know, now going back to the sum variable, I where n is t over delta t, about this. So from here, we know we have that expectation of each of these is 0, because you have xi takes +1 and -1 with equal probability. So the expectation comes out to be 0. And variance comes out to be one. So therefore, using the properties of expectation, we will have expectation of this is linear in these is a 0, and variance the variance formula, if you have like this, then the constants, when they come out, they get squared. This becomes into x square, and this is your variance, and you can also write it like, because n is t over delta t. Now you want this variance to be some finite number. We should take a limit so that the variance is finite. So over here, so we have n is going to infinity. So you need to do something so that the variance should remain finite. This implies that the step size, they should be going to 0. So essentially, you have to take when this goes to 0, this goes to 0, the ratio is finite. And I just give it a name sigma square. Then the variance, which I just computed, to be this will become sigma square t. So the step size goes to 0, and the time in which you take step, that goes to 0, so it becomes a continuous process. But to take that limit, you have to keep this t out, and what you find is that the variation of this variable, it becomes it depends on t. It grows linearly with t. So you have shown that the limit of random walk is Brownian motion. This is the variable sigma under root t, which is the standard normal variable. And this is your standard normal. Remember, this is the formula. This is 0 for us. And this is the Sn of t. And this is its variance. So that means that this Sn of t, it's PDF is normal PDF. No, we had in this definition call that normally distributed. With mean 0 and variance sigma square t. So what this essentially says, each increment is independent of the other. So this is also a property. This is the Markov property. Of the random walk. So what it means is that if I check a process going through a random walk at various times, then wherever this particle was at these times, it doesn't matter at all. At T6, I can just pick any one of them if I know where it was at T5. This is just a normal variable with mean 0 and variance if I look at this guy and knowing that where S of T5 was, then this is normal. with mean. This becomes the mean, and variance that means as soon as we put condition that s of any one of them, let's say here we're talking about some number b, what happened before becomes irrelevant. So it's just renewed. You can just look at it from any one time and move forward from there. So this is the Markov property. And it has consequences. For example, if I want to write it, I can also write it this way. Okay, let me- So I can write it this way, that the PDF of the uh, PDF of the this of this process, which is the Brownian motion, if I evaluate it at different points, it would be f of t1 x1, f of t2 times f of t3 minus t2 where each one of them if f of t is simply for a standard Brownian motion. So if I'm writing, for example, this guy, it would be what's happening is you are checking it at different times. And you are giving the PDF that what if it's at x1, it's at x2, over here it's at x3, over here it's at x4. What is the probability? So from what we have said is that the probabilities, they're gonna be, because this is gonna be the mean. So it will be the difference, this difference, which will come in the standard normal. And you will just construct a normal out of this difference. And its standard deviation will be controlled by this interval. If this is large, there would be larger jumps. And apart from that, it's a product. So you have a joint distribution defined. And since you have joint distribution defined, so you can then extract all the properties you want from this about this process. For example, let's do an example. So suppose you want to compute the covariance. So suppose example. Suppose B is usually used to write the standard Brownian motion. Process find the covariance of this process at two different times. So how are they related? So using the formula for covariance, I have to compute this. Now this is simply 0 because these are the variable bound and variable at any time ts. You can think of it from the 0 mean, and we know that this mean is going to be 0. So this is the main thing which we have to compute. So to compute this, what we can do is, suppose S is less than or equal to T, and write BT I just added BS and subtracted BS. But the nice thing now is that this is a normal variable and this is a normal variable. These two are normal variables. And they are independent. By Markov property. BS and BT are not independent. It's the successive intervals which are independent. Successive jumps. So like this is you can think of it as you checked at 0 and you checked at S. There was this jump, and now at T you have another jump. So this jump and this jump, cumulative jump, they are going to be independent. So having written it this way, all we need to do is to compute the covariance. I needed this. So now expectation of BSBT like this. I need this BTBS. Oh, but this BT is BS is being multiplied by BS. So you get expectation of BS square plus expectation of BS with BT minus Bs. Now the point is that these chi Bs and Bt minus Bs are independent. That means that this expectation breaks down. This is 0 and this is 0. So this term is 0. While expectation of the square, this is a normal variable, so this is just equal to the variance of Bs. And variance of Bs we know is just equal to the length of the time, which is S. So that means that the covariance of Bt Bs is equal to S if S is less than equal to T. Now, if I repeat this process, assuming T is less than or equal to S, obviously this will just, that will give me so that means that the covariance of Bt Bs is just minimum of T and S. Now, one can also compute, for example,